Okay, problem 3. Let's read it together. Tim measures the position and time of his radio-controlled car and obtains the data table shown here. So, part A, draw a graph of the car's position versus time. Remember to do these things. Label and scale your axes, include units, plot points, draw the line of best fit through the data. Alright, so at a time of 0, position of 0, time of 1, position, they're giving you at what time it's at a certain spot. We have to show that on this graph. So this position column, this is what's going on this position axis. So if you look, our largest position got to 39.2, so almost 40. We need to scale this axis to fit 40. So looking at what I have, what I'm going to do is treat each box as 5. So this would be 5, but that would be 10, right? So this would be 20, 30, and 40. You don't have to use that same scale, but make sure you can fit the entire data on your graph there. Alright, for time, we have 7 seconds in total. There's not too many boxes, so I'm just treating each box as a second. So 1, 2, 3, 4, 5, 6, 7, 8. Alright, now you just have to plot your points. So at a time of 0, it was at a position of 0. 0, 0 is our first point. At a time of 1, it got to a position of 0.8. 0.8 is still really close to 0. Remember, our first box represented 5, so 0.8 is still really close to down here. It hasn't moved very much at all. In 2 seconds, it got to 3.2, so we're even higher, but we're still not even to that first box yet. We're still not even to 5. In 3 seconds, it's at 7.2. So over to 3, up to where 7.2 would be. Now we're finally past 5. We're kind of halfway to 10 now. And just continuing the same process. So 4 seconds was 12.8, somewhere in there. 5 seconds, we're exactly at 20. In 6 seconds, we're at 28.8. So almost to 30. And then 7 seconds was that 39.2, right below 40 basically. Okay, so we just plotted the points. They also wanted us to draw a line of best fit through the data. So it's not going to be a straight line, obviously, because you see it starts off flat and it curves steeper upward. So try to make a nice smooth curve through those points. Let's see how well I do here. Alright, kind of like that. It's getting steeper and steeper as time goes on. Okay, something I forgot to do, and this is for points, you must include the units. So they labeled position and time. They labeled the two axes for you, but you need to say what units they were measured in. So position was measured in meters. So make sure to the side here, you tell me what it was measured in. Time measured in seconds. Okay, that graph will give you full points on the test. Okay, part B. Calculate the velocity of the car at t equals 5 seconds. Show your calculation in detail. Alright, we don't know the acceleration of the car, so what you're going to have to do is use the graph to find the velocity. On a position graph, velocity is slope. But if you notice, it starts off flat and it's getting steeper and steeper and steeper as time goes on. The slope is changing. So to find slope, what we're going to have to do is make a window of time. It's been a little while since we've done this. So we're making a window of time that's centered at 5 seconds. So you can do a window from 4 to 6. You can do a window from 3 to 7. It's up to you. Okay? I'm going to use 4 to 6. So from 4 seconds, it's at this position. At 6 seconds, up here, it's at that position. What I want to do between this point and this point is find my rise divided by my run. Okay, so rise divided by run. Between those 2 points will give me the velocity at 5 seconds. Now it's hard to see exactly where these points are on your graph, but remember, they're at the position that it told me in this data table. At 4 seconds, it was at 12.8. It went up to a position of 28.8. So from 12.8 to 28.8, the rise, how much it changed by, is 16. If you can't do that in your head, just subtract the 2. Final minus initial. 28.8 minus 12.8 gives you 16. Okay, so our rise is 16. The run is just from 4 to 6 seconds. So from 4 to 6, 6 minus 4 gives us 2. Our rise is 16, our run is 2. So the velocity at the 5-second point is rise divided by run. And 16 divided by 2 gives you 8. So that's my answer for part B. 8 is the velocity, and make sure you have a label for that. My rise was in meters, my run was in seconds. So when you divide rise divided by run, it's meters per second. That's our answer for B. Okay. The next problem. A spaceship is landing on the moon. Its distance from the surface is shown in this x versus t graph. Part A. In words, describe the ship's position, time, motion. Include starting point, direction of motion, and information about velocity and acceleration. Alright, so looking at this graph, let's list each of these things in order. Starting point. So you should kind of remember, starting point, that's the position you start at. So x is position, I is initial. Position initial is what they're talking about. So let's look at the graph and find out. Our position initial is here, starting up there. Now there's no numbers on the graph, so we don't know what number to put here, but we do know this is 0 at the axis. It's above 0. So the one thing we do know about that starting position is that it's positive. Starts at a positive location. The second part, direction of motion. From that positive location, it goes downward. Downward on a position graph would be our negative direction. So that's what I'm going to say for direction. Since it's going downward, my direction of motion is negative. Okay, the next part they want, information about velocity and acceleration. So for velocity and acceleration, you need to talk about some stuff. Velocity. On a position graph, velocity is slope. So if you notice, it starts off very negative. It starts off steep, slopes downward. At the end, it flattens out. So as time went on, it kind of got flatter and flatter. The slope decreased. So that tells me that my velocity, it's downward, so it is negative. And since it flattened out, that means the object was slowing down. So it's negative, and this velocity is decreasing. The slope flattened out. My acceleration, the rule is, if something is slowing down like it is in this problem, the velocity is decreasing, then my acceleration must be opposite of what my velocity is. So my acceleration for this problem is actually positive. And since it's a nice smooth curve, it's telling me that this is constant as well. Great. Alright, now we have to make a velocity graph that matches this motion. Draw a velocity time graph of the ship's motion. Be sure to include the units. So those are left blank for a reason. Let's do that first. If this was in meters and seconds, that means our velocity should be the same, meters per second. Our time on this graph would just be in seconds. So that's a point already. Now we need to show what this should look like. Look at your slope. At the beginning of this graph, the slope is very negative. So that's telling me my velocity, it doesn't start positive, it doesn't start at 0, it starts negative. The slope starts negative. As time goes on, it flattens out. At the end, my slope is completely flat. If you have a slope that is flat, it has a slope of 0. So at the end of my motion, there's a slope of 0. Your velocity graph should start negative, and as time goes on, the speed decreases to 0. Okay, so that should have been your velocity graph to match that motion.